Hello and welcome to the next class of the course Basics of Semiconductor Devices and Technology. So far we have been considering a very general crystal and we applied all the understanding or all the concepts that we studied in quantum mechanics in case of a general crystal to determine some of the characteristic in terms of how electron would behave in a single crystal lattice. Now going forward, we will be applying all these concepts, particularly in terms of semiconductor material, to identify the behavior of devices. So behavior of the electron and holes in case of semiconducting devices, and that's how we will try to derive device characteristic out of it. Like in the last lecture, we studied density of states or density of quantum states, definition of conduction band, valence band, density of quantum states in valence band, density of quantum states in conduction band, Fermi-Dirac probability, so we will use all of that, and we'll try to derive relations now in this module for concentration of electrons and holes in conduction and valence band. And we will do it for intrinsic semiconductor, which means there is no intrinsically there is no doping or external doping involved, and also do it for extrinsic semiconductors, which means that the semiconductor has got some external dopant introduced, and those dopants are going to make the semiconductor rather a n-type or a p-type kind of a semiconductor. So we will also apply the concept of Fermi energy in that we studied in the previous module in the process of deriving all of these. In general, in this module we will deal with semiconductor in equilibrium. Equilibrium means we are not applying any external excitation or we are not changing the state of the system by external excitations. So if, for instance, if we are dealing with a finite temperature, the temperature will not change as a function of time. If we are and of course in general we are not applying any external stimulus or bias. So that's the definition of the equilibrium. So overall in this module we'll try to derive thermal equilibrium concentration. So again, here the thermal equilibrium means the system is in thermal equilibrium. There is no thermal fluctuation or thermal variation across the device, across the system. And of course it's an equilibrium in general because there is no external stimulus in terms of external field or magnetic field, electric or magnetic field or temperature gradient, as I said. So we'll derive thermal equilibrium concentration of electrons and holes in a semiconductor, in general a semiconductor, as a function of Fermi energy level. We'll do that we'll show it for intrinsic semiconductors and also for materials which are doped. So basically the doping process will be introduced, and I'll show you favorably how dopants are introduced and how a dopant can make the material n-type or the p-type. Then once the dopants are introduced, we'll also derive the thermal equilibrium concentration of electrons and holes in semiconductor as function of concentration of dopant atoms added to the semiconductor, and in the end we'll discuss all these concentrations for intrinsic or extrinsic semiconductor as a function of the position of Fermi level, and we'll also talk about the relevance of the position of Fermi level in terms of identifying the doping or identifying the conductivity type N or P type of the semiconductor material that we are dealing with. Okay. So in the previous class we studied the definition of the density of a state and the Fermi-Dirac distribution, and what I told you is that the Fermi-Dirac distribution, which is Fe, is the ratio, and of course if you are calculating probability, that's how the ratio comes into picture, the ratio of the concentration distribution and the density of state. So from this relation, of course, you can calculate the concentration relation as a function of energy as well, and that is nothing but the product of the density of state and the Fermi-Dirac distribution. Now if you want to find the total concentration, you have to integrate for the entire energy range. So if it is conduction band, you integrate from the conduction band edge to the infinity, which is this point, to all the way up to infinity. So the area under the curve resulted from the product of density of state and the Fermi-Dirac distribution, which is the electron concentration as a function of energy, if this is conduction band, is the total electron concentration inside the conduction band. So now what do you see here? You see, so for the time being ignore the bottom portion. You see that I have plotted the Fermi-Dirac distribution, which is this light blue line, and this is plotted as a function of energy. So earlier you have seen F being on the y-axis and energy being on the x-axis, and in that case it was a function, it appeared something like this. Now we have just flipped it, so we have rotated it, so the energy goes here, F comes here, so it looks like something like this, right? And somewhere here is the Fermi energy level, EF, which is this. Now why I did this? I basically rotated the axis so that I can plot the conduction band density of a state along with it, which will help us taking the product in a easy fashion. So the other thing which I have, earlier you have seen the density of state function, for instance. The density of state looked something like this. If this is E and if this is G, yeah, it's something like this. Yeah, let me correct it. This is E, this is G, it's something like this. Okay, so now again the same has been flipped, so you see the density of state plotted. So this axis is both G as well as F, so that we can make a product, and this axis is the E. Now if you take a product, what do you get? This axis here shows N as a function of E. So this is E, and this is N. So what it shows that the electron concentration starts increasing. It's maximum at an energy level slightly higher than conduction band, and again it falls as you go higher and higher in the energy level. It falls because the probability of occupying any state would fall as you go up in the energy level. Though you have a higher and higher density of state available as you go up in the energy level, but since the probability of occupying a state would reduce as you go up in the energy level, the net product would also fall as you go up in the energy level. However, since they both are competing, there is a point which gives you the maxima. The maxima is not at the conduction band edge, and also not as you go up in the energy level. Now the area under the curve of this shaded region will give you the total electron concentration inside the conduction band. Let's analyze the same for the case of holes. So for the case of holes, what is important? We need to look into the number of states which are being unoccupied. Now number of states being unoccupied is 1 minus f. F is the probability an state is occupied, and 1 minus f is the probability an state is unoccupied. So in valence band we are talking about holes. Holes means those states which are not occupied, and the conduction in the valence band, you remember, happens through the states which were not occupied. So the electron moves from an occupied state in the valence band, which is the covalent bonded region, to an unoccupied region, which means the region where, or the bond where the covalent bond was broken. So the electron conduction in this case happens through the hop in hop off of these electrons from occupied to the unoccupied states. So the conduction or the number of holes are a function of the number of states which are unoccupied, because the electron is going to hop through that, so that unoccupied state is represented as the hole over there. Okay, so 1 minus f is the state or the number of states, or the probability of a state being unoccupied. Then GV is the density of a state in the valence band. So the total electron or the total hole concentration in the valence band is the product of the number of unoccupied states times the density of state in the valence band. A zoomed region of this thing is presented here. So what you see is, this is the density of state, this is the Fermi function for a hole or for a electron being unoccupied or a state being unoccupied, which is 1 minus f. And if you take a product, what you get again a very similar function as we have seen before for electrons, a very similar function. However, in this case the hole concentration would first increase as you go below in the energy level, below the valence band, and you find a point where you have a peak. The peak is not at the edge of the valence band, the peak is also not as you go lower and lower in the energy levels, and you get a region which consists of holes. And if you want to find the total number of holes, you have to take the area under the curve, area under this curve, which means you have to integrate this from minus infinity to the valence band edge, right? So this is the integral from minus infinity, which is somewhere here, sorry, minus infinity all the way up to the valence band edge. Okay, so hope you understood the pictorial representation. Now let's see how to do it. So the electron concentration, as I said, is the product of Fermi-Dirac distribution and the density of state. If it is electron, we are talking about density of state in the conduction band. Now you can recollect both the functions. If you have to calculate the total number of electrons in the conduction band, the thermal equilibrium concentration of electrons, keep in mind these terminologies: thermal equilibrium concentration of electrons. Some of these terminologies may become a bit confusing later on, the equilibrium concentration, non-equilibrium concentration. So keep in mind we are talking about thermal equilibrium concentration of electron. There is no external stimulus, there is no temperature gradient across the material, across the system. The temperature is fixed, constant across the entire system that we are dealing with. So if you have to calculate the thermal equilibrium concentration of electron, you have to do if this is of course one dimensional function of energy, so you have to do a line integral of the product of the density of state in the conduction band and the Fermi-Dirac function, integrate it from the conduction band edge to the infinity. I'll skip the maths, that's pretty simple. You feed both the values as you have seen in the previous module and you do the integral. What you get is this. However, keep in mind we have taken an approximation here. The f that you use for doing the integral is the Boltzmann approximation of the Fermi-Dirac function. The Maxwell-Boltzmann approximation of the Fermi-Dirac function will give you this relation, and going forward as I also told you in the previous module, that always remember the assumptions. Going forward, we will always assume for easy maths. Of course, if you have more sophisticated tools like numerical tools, then you can use the complete Fermi-Dirac function. But if you have to do maths with pen paper for easy assessment and quick assessment of device physics and so on, it's easy. It's better to simplify the Fermi-Dirac function into the Maxwell-Boltzmann distribution function, and then do the integral. And if you do the integral with that assumption, this is what you get. So here NC is nothing but a constant. You get NC because if you feed all the values for GC and FE and all, you collate all the constants together, what you get is this. So this function is denoted as NC. NC is the effective density of state in the conduction band. So here C signifies the conduction band, and capital N signifies the effective density of a state. So NC is the effective density of state in the conduction band, and as you notice here, all the parameters, whether it's the effective mass of electron in the conduction band, Boltzmann constant, temperature, Planck constant, they all are constant. So therefore the effective mass of, or the effective mass in that particular material is going to define the effective density of state in the conduction band. The only parameter which will be dependent on the semiconductor material that we are dealing with is the effective mass of the electron, in this case in the conduction band. So as the effective mass changes, the effective density of a state in the conduction band will also change. As the effective mass increases, the effective density of a state increases. So keep that in mind. Effective mass, you may notice from the previous module that effective mass may adversely affect the transport. It may slow down the movement, which means it may slow down the velocity, which means it may lower the current. But at the same time, the effective mass, higher the effective mass will give you higher density of state, and higher density of state means you can have higher number of carriers present in the conduction band, which means that that will allow a higher conduction or higher level of conduction through the conduction band. If this is electron, and the same is valid for the holes. So in that sense, the role of effective mass is very important when it comes to the density of state or the effective density of state. Now, if you assume that the effective mass is same as the mass of free particle, then the effective density of state turns out to be 2.5 into 10 to power 19 per centimeter cube. What does it mean? It means that there are 2.5 into 10 to power 19 states available per centimeter cube for an electron to be occupied, right? Of course, if effective mass is higher than m naught, this number will be higher. If effective mass is lower than m naught, this number, the NC will be lower. Okay, now the same maths you can do for holes. The only difference in this case, as I said earlier, for holes you have to take a product of the available states, or the probability of a state being unoccupied in the valence band, and the available states or the density of states of holes, or the density of states for the valence band. Now you take the product, that will give you the whole concentration as a function of energy, and if you want to find the total thermal equilibrium concentration of holes in the valence band, what you have to do, you have to take this integral, and this integral is from minus infinity to the valence band H. You please correct this. This is minus infinity to the valence band H. So we do the same maths again. You feed the values as you have seen in the previous module, and if you do the maths, what you get is this. This is NV times an exponent, a function of EF minus EV. So basically it's inversely proportional to the gap between the Fermi level and the valence band H, right? And here NV is again the effective density of a state of holes in the valence band, and this again in the same fashion depends on the effective mass of the holes. As the effective mass increases, the effective density of a state in the valence band will increase, and vice versa. If you consider mp star equals to m naught you can guess you would get the same number. Now if you consider this mp star as a number which we have seen for silicon, what you get is 1.04 into 10.19 per centimeter cube. So as you see that for in case of the electron this number was higher than 2.5, and in case of holes this number is close to 1, so there are more electrons or there are more states present in the conduction band versus the number of states present in the valence band for the holes. Another thing which is important to analyze here is the total hole concentration, or in the previous case the total electron concentration is a strong function of the gap between the conduction band and the Fermi energy level. In case of holes it's the function of the gap between Fermi level and the valence band, which means as you can see as the hole concentration will be maximum, or in the previous case the electron concentration will be maximum when this gap, when the EC and EF gap is 0. So if I plot here, if this is EC and if this is EF and somewhere here is EV, so if this gap is 0 then the electron concentration in the conduction band will be maximum. Of course this gap can be positive as well. We will discuss about the degenerate semiconductor a little later, where the Fermi level can be inside the conduction band, and in that case the electron concentration in the conduction band can be higher than of course mathematically can be higher than the value that you see here, but usually of course the numbers will saturate as that's not the practical scenario. So in all cases if we say that the gap is 0, the electron concentration is going to be maximum. Similarly in case of holes, if we say that if this is conduction band, this is valence band, this is Fermi level and this conduction band, if we say that this gap is 0, the electron concentration is maximum. As this gap increases, as the Fermi level moves away from the valence band, this whole concentration will reduce. Similarly in the previous case, as the Fermi level moves away from the conduction band, the electron concentration will reduce. Okay, so let's look into a numerical problem. So the problem is that you have to calculate the probability that a state in the conduction band is occupied by an electron, and you have to calculate the thermal equilibrium electron concentration in silicon at 300 Kelvin. So you see you have got silicon. This will help you in defining, let's say, the effective density of state. You have to find the thermal equilibrium electron concentration, the method just we followed in the previous slide, and before that you have to calculate the probability that a state in the conduction band is occupied. Now the probability is nothing but the Fermi function. You remember the Fermi function we have seen in the previous slide. You can, if you want, you can simplify this into Maxwell-Boltzmann distribution, and then what it says, the Fermi energy is 0.25 electron volt below the conduction band, which means EC minus EF is equals to 0.25 electron volt. So EC minus EF is going to be 0.25 electron volt. You know KT, right? So you can feed all the values here, and what you get is the probability of a state being occupied if the Fermi energy is 25.25 electron volt below the conduction band. Now going to the next step, we have to calculate the electron concentration. You remember the relation that we derived in the previous slide. The electron concentration is effective density of a state times exponential of the gap between the EC and the Fermi level divided by KT. You feed all the values here. The NC value we saw earlier. What you have to do, you remember the NC value, that was 2.5 into 10 to the power 19 per centimeter cube, and this was when m star equals to m naught. You also remember for silicon we saw that m star for silicon in case of electrons is 1.08 m naught. The NC has m star to the power 3 by 2, as you remember from the previous slide. So all you have to do is you have to calculate this additional factor, which is 1.08 to the power 3 by 2, and this will be multiplied with this NC, becomes the effective density of state of the of electrons or of conduction band in case of silicon. So you feed that value here and you put the exponents and you get the electron concentration in this particular scenario, which is 1.8 into 10.19 per centimeter cube. Okay, now let's look into the next problem. Calculate the thermal equilibrium hole concentration in silicon at T equals to 400 Kelvin. Now note that now we are dealing with a temperature higher than the room temperature, and you may notice that the numbers would vary. Here you assume that the Fermi energy is 0.27 electron volt above the valence band, so EF minus EV is equals to 0.27 electron volt, and you have to assume the value for NV value for silicon at 300 Kelvin is given, which is 1.04 into 10 to the power 19 per centimeter cube. So we have got the value for NV at room temperature. We have to now find the value of NV at a higher temperature. So how do we do it? We if you remember, NV was also a function of temperature, and so to calculate from the room temperature value, if you go back, now you see the NV is also related to temperature to the power 3 by 2. So if you have value at 300 Kelvin, all you have to do is use the 300 Kelvin value times the additional factor, which is 400 divided by 300 to the power 3 by 2 is what you have to multiply into this value, which is NV 300 Kelvin. So if you do that, if you do the maths, you get 1.6 into 10.19 per centimeter cube. Now another thing to analyze here is that if you notice, NV at room temperature is 1.04 into 10.19, and as you increase temperature you get more states, or you get higher density of state being available in the valence band. This is also because you have now higher probability of occupying, the probability function will smear out, so effectively you have higher density of state available in the valence band. The KT value is something that you can figure out for 400 Kelvin. At 300 Kelvin it is 0.0259 electron volts. So for 400 Kelvin it is nothing but this times this value, 300 value Kelvin value times 400 divided by 300, which is the multiplication factor here. So it becomes 343 0.3 milli electron volt, or in other words 0.03453 electron volts. So this will be, please ignore what I said, 34.53 milli electron volt, and at room temperature it is 25.9 milli electron volt. So we feed all these values back, we got the value of KT, which goes here. This is something which you already know, which is 0.27, and NV is something that we already calculated here. So you feed all the values here and you get the whole concentration, which is 6.43 into 10 power 15 per centimeter cube. Now as an assignment, you calculate what the whole concentration will be if temperature is 300 Kelvin, and you make a comparison, and you will notice that this number is different. Okay, so having looked into some of the numerical problems, hope that would have given you some feel for the equations and the derivations that we dealt with before. Now let's talk about intrinsic carrier concentration. So what is intrinsic carrier concentration? At finite temperature T, you remember we started with this concept where you had a valence band, conduction band, you had a valence band, and some of these states from the valence band were emptied and these electrons moved to the conduction band. So this basically resulted into a finite number of holes. Let's call that as intrinsic number of holes or intrinsic holes, and then it resulted into some finite number of electrons. Let's call that intrinsic electrons. So these intrinsic electrons and these intrinsic holes, can we find what should be the value of these intrinsic electrons and holes? So let's assume that under this condition, when we are not doping in externally, the Fermi level is at a certain value. Let's call that EFI, which is the intrinsic Fermi level. So if we use the previous relations for electron and hole concentration, and if we replace EF, which is the Fermi level, by EFI, which is the intrinsic Fermi level, we should be able to get the intrinsic, which is Ni, and if we say that both Ni and Pi are same, so we can, if we say that both Ni and Pi are same, then we can call it Ni as a common term, right? So this is also Ni, but let's not do it for the time being. Let's just use the term N naught and P naught and take a product. If we take a product, what we get NC NV, we get the exponents multiplied, and you would notice that in the exponent, this factor, which is minus EFI, and here it's plus EFI, will cancel out. So what you get is the difference of the conduction band and the valence band, and you know that the difference of conduction band and the valence band is nothing but the band gap of that particular material. So the Ni square, which is the product of N naught and P naught, the Ni square is equals to N naught times P naught is Nc Nv, which is the effective density of state in the valence and the conduction band, exponent of minus Eg by Kt. And as you know, Eg is a constant, is a material parameter, and Kt is also a constant, and Nc Nv are also a constant. So which means that Ni or Ni square is a constant at a given temperature, or in other words, it's a function of temperature and function of the other material parameters. If the material is constant, then it becomes a function of temperature. So as the temperature changes, the Ni value will change, and as you can see here, Ni is proportional to exponent of minus 1 over T, of course in the under root. So as the Ni value or as the temperature value increases, the Ni value will also increase. Let's see that in the next slide. So if you can feed all those values back, if you feed the value of Nc and Nv here, as we have seen, the value of Nc and Nv also depends on the temperature. So if we are talking about Ni in terms of temperature, it's important that we further divide Nc and Nv in terms of effective mass and the temperature. So if you feed all the values, what you see, the Ni square is a function of Ni square is proportional to temperature to the power 3 and exponential of 1 upon T. Now this is very important because in the previous slide I told you that it looks like it's exponent of or inverse exponent of temperature, and therefore if temperature increases Ni should reduce, but now you got another parameter, another factor, which is temperature to the power 3, and this may cause Ni to increase as a function of temperature. So the same has been plotted here, and if you see as a function of inverse of temperature, or if you see here as a function of temperature, as the temperature increases, as the temperature increases, the value of Ni also increases. And this is very important to note because Ni at room temperature is something of the order of 10 to the power 10 per centimeter cube, and as you increase the temperature, the Ni will increase, and it happens in in situations when we are dealing with the semiconductor material under very high temperature conditions. And if the Ni increases of the order of the background doping, the doping that you have introduced for electrons or holes, then the function of the semiconductor device will be seriously affected, and if Ni exceeds the background doping, the device will not behave same as the intended device, right? And as you can notice, this is a strong function of the effective mass and the band gap. So it's obvious that the Ni would be different in different materials. If it is silicon, the Ni is of the order of 10 to the power 10 per centimeter cube. If it is gallium arsenide, Ni is of the order of 10 to the power 6, and if it is germanium, the Ni is of the order of 10 to the power 13 per centimeter cube, all at room temperature. Okay. So now coming back to the point which I earlier said, that in an intrinsic semiconductor N naught and P naught must be same, because as I said that you have these conduction band and the valence band, and you have these emptied states and they all move to conduction band. So this becomes available free electrons in the conduction band. So the number of available states in the valence band, which is the number of holes in the valence band, must be same as the number of occupied states in the conduction band, which is the same as the number of electrons present in the conduction band. So for an intrinsic semiconductor, N naught must be equals to P naught, and if it is N naught is equals to P naught, you can basically equate both the terms. And what we will try to see whether the Fermi level is at the mid gap. So what is mid gap? Let's say if I draw a point and call it mid gap, let's say I call this as E mid gap, and if this point is EC and if this point is EV, then EM is nothing but EC plus EV divided by 2. So let's see if the Fermi level or the intrinsic Fermi level is same as mid gap. So is EFI equals to EM is the question, is what we are trying to find here. Or in other words, we are trying to find where the intrinsic Fermi level will be in reference to the mid gap position or the middle point of the band gap region. So for that we equate both N naught and P naught. And if you do the maths, if you simplify, you take out EFI is the common factor here. So if you do the maths, you take out EFI equals to 1 by 2 EC plus EV plus 1 by 2 KT log NV by NC. EC plus EV by 2 is the mid gap point, so as we see here is the mid gap point. And if you simplify this further, if you take if you divide this, you remember that everything else in NV and NC was common except NV was function of effective mass of holes to the power 3 by 2, and NC was a function of effective mass of electrons to the power 3 by 2. Rest everything else will cancel out, so this 3 by 2 will go out, so this becomes 1 by 2 times 3 by 2 will becomes 3 by 4, and log of MP divided by Mn and KT. So if I rearrange it, EFI minus E mid gap is a finite number and is proportional to the ratio of the effective mass of holes and the effective mass of electrons. Now if MP is equals to Mn, then this becomes 0 and this becomes 0. So only when effective mass of electron is same as the effective mass of the hole in a given material, the intrinsic Fermi level will be aligned to the mid gap point. Otherwise the intrinsic Fermi level will always move towards the lighter particle relative between electron and hole. So if holes are lighter, the intrinsic Fermi level will be closer to the valence band, and if the electrons are lighter, the intrinsic Fermi level will be moving or will move towards the conduction band. Okay. So far we discussed everything in context of intrinsic semiconductors. And now the question is, what happens if we dope the semiconductor? Now, doping means we are introducing atoms which basically introduce, or we are introducing impurities So far we talked about the semiconductor which was intrinsic in nature. Intrinsic means we did not introduce any impurity. But now the question is, what happens if we introduce impurities in the semiconductor? Now, these impurities, again depending on what we are doping the material with, but if we talk about silicon, we often want to make the material N type or P type. So if you want to make N type, we basically use donor type impurities or pentavalent impurities, and if we want to make P type, we usually use acceptor type impurities, which are trivalent impurities. Now the donor type impurities are phosphorus and arsenic, and the acceptor type impurities are boron and aluminium. Often we don't use aluminium in case of silicon as far as the regular process is concerned, but aluminium can become an unwanted or unintentional dopant in case of silicon, which would adversely affect the performance. But let's focus on phosphorus, arsenic and boron. Now why something is called donor? Because if you introduce arsenic or phosphorus, it will donate an electron. Why something is called acceptor? Because if you introduce boron, it will dissipate, or it will basically take out an electron, or it will dissipate a hole, or it will produce a hole. Now classically, this is the picture you are aware of, that let's say a silicon atom is replaced by a phosphorus atom by certain mean. It would liberate, it would introduce, or it would basically produce an extra electron in the crystal lattice. And if you dope by boron, in this case, by the way, it can also be arsenic, and if you dope by boron, then it would, because the boron would bond with three adjacent silicon atoms, right? In this case, this one and not this one. So basically one of the covalent bonding is vacant, and that can be seen as a vacant bond or vacant state, and therefore you can say that the boron is going to basically introduce a hole in the system. In case of phosphorus, it had 5 valence electrons, so the 4 are going to contribute in doing this covalent bonding, and one of the electron will be available as excess and will be available to move around in the crystal lattice if the system has attained a certain temperature required for this electron to be moved out of the valence shell of the phosphorus. Now this is the classical picture. Quantum mechanically, what happens if you introduce these dopings? You can assume, or you can visualize that locally in this region, the band structure would get altered. Now what happens to the band structure in that local region? The band would actually experience another energy state being introduced below the conduction band if it is phosphorus, and if it is boron, it would notice another energy state introduced just above the valence band. Now this energy state will have a finite probability of occupying electrons. This energy state above the valence band will have a finite probability of capturing electrons. Now if the temperature is higher enough, or in other words, if the total energy across the system is higher than the gap between conduction band and the energy donor energy state introduced, then all these electrons will move to the conduction band. Like earlier, because of thermal excitation, the electrons from the valence band move to the conduction band. In this case, all these electrons which were present in the donor state will move to the conduction band. Similarly, if there is enough system energy available or energy available in the system, which is proportional to the gap between EA minus EV, which could also be a thermal excitation, then all the electrons will actually have, or these electrons from the valence band will actually get captured in this acceptor state, and therefore it will leave a hole in the valence band. So that's how the electrons or the holes are introduced when an impurity is introduced in the system. Okay, so let's try to get a feel for what is the ionization energy for these dopants, and for that you can actually figure out what kind of how far these excess electrons are, and what kind of energies are required in or what kind of binding energies are associated with this, and therefore if you know the binding energy, you know what kind of energy is required to get the electron out of the valence shell and dissipated or present in the crystal lattice to move around. So for that, we just do a quick maths. You can assume that an electron, if it is bounded with the valence shell or the core of the atom, or the nucleus of the atom, the forces which are basically responsible for that are the Coulomb force of attraction between the electron and the ion. So in this case, this could be the phosphorus. If let's say we talk about the phosphorus, it could be the phosphorus atom or phosphorus ion, and the electron in the outermost shell, and of course the centripetal force which is responsible for the electron to orbit phosphorus, right? So now if you equate, so the electron is still orbiting phosphorus, which means that these two forces are equal. So you can write the Coulomb force of attraction, you can write the centripetal force. Here this is the magnitude of the velocity, and this is the radius, which is this. Okay, so if you rearrange it, and you can assume that the angular momentum is also quantized, because it's moving in a well-defined shell. So you can write down a relation for the angular momentum. So that angular momentum relation will give you the value of the radius, going back from this. And if you remember, the Bohr's radius was close to 0.53 angstrom. So you can take the radius or the ratio of this radius and the Bohr's radius, and you will find that this is related to the n square, which is this n, epsilon r, the ratio of the effective mass, and the mass of the particle in free space. If you take the closest energy state, which is n equals to 1, you will find that this ratio comes close to 45, which means the radius, let's say in this case, is close to 23.9 angstroms. So this is the radius corresponding to close to 4 lattice constants of silicon, and that's the reason, already if you noticed, in this case the electron which was given out by the phosphorus was shown several lattice constants away from the phosphorus atom. Okay, so now you can see that how far this electron is compared to the phosphorus impurity or any other impurity, and if it is too far, you can imagine that making this or getting this leave the valence shell is not going to be a very difficult task. So you can also calculate the energy required to release the electron or hole from the dopant, and that energy you can calculate based on the total energy associated with that system first, which is the kinetic energy and the potential energy, and if you do the maths, you get the total energy, which is the energy associated with that ion in that case. And if you feed all the values here, in case of silicon, for instance, what you get is 25.8 milli electron volt, Now this is negative, which means this is the binding energy, and you need a positive 25.8 milli electron volt, which is very close to room temperature, for these ions or these electrons to be dissipated out of the phosphorus. And once they're out, they're out. So basically you just have to heat up the system, anneal the system, and you get these electrons freely available in the crystal lattice to move around. Okay, so that was a quick overview of what happens when you dope the semiconductor, and from where these excess carriers do come. So we talked about the classical picture, and then we also discussed about the quantum mechanical picture. Now let's try to do the same maths as we did earlier for these extrinsic semiconductors. So extrinsic semiconductors are the semiconductors which have these excess or external doping or these impurities being present inside the semiconductor. And these extrinsic semiconductors, as I have already shown in the previous slides, that are going to introduce excess electrons or excess holes. These excess electrons are the electrons which come out of impurities like phosphorus or arsenic, and excess holes are those extra holes which come out because of impurities like boron introduced in the semiconductor. So we'll see that how to calculate the excess hole or excess electron concentration if you are doping the semiconductor with these impurities. Now you can imagine that the maths must remain the same, right? I mean, all what is going to happen is that some of the energy levels are going to be changed, but the maths must remain the same. The density of a state was related to the semiconductor material. It's not related to the external impurity. So the density of a state must remain the same. The Fermi energy level may change, but the Fermi-Dirac distribution is just a distribution function. It has nothing to do with what semiconductor material we are dealing with. Of course, the distribution function will be different if the Fermi energy level changes, right? And you also remember that the Fermi energy level, we talked about the reference point, or the point where the Fermi energy level should be, and I told you that if you have extra electrons, the Fermi energy is going to be closer to the conduction band, and if the system has more holes, the Fermi energy is going to be closer to the valence band. So that's exactly what happens in this case. The Fermi energy will shift. Fermi energy will get closer to the conduction band if it is N type doping, and the Fermi energy will shift to the close to the valence band if it is P type doping. Now if it is N type doping, of course the electron concentration will go up. So as you can see that the area under the curve in the conduction band for the electron concentration is higher, but similarly the hole concentration will go down, and we will see the maths. Similarly, if you are doping with P type, the hole concentration will go up, but since the Fermi level has shifted down, the probability of an occupying a state in the conduction band for this particular material will go down, and therefore this area under the curve will go down. Similarly, for the N-type semiconductor, as I said, the hole concentration will go down. That is because if the Fermi level has shifted closer to the conduction band, this tail would cause a lower magnitude when you take a product of the Fermi function with the density of a state, and therefore this area under the curve will go down. Okay, so we can do this maths. Again, we use the same relation, and in this case it's not EFI, it's EF, and for holes again it's EF, it's not EFI. Now this Fermi level is the true Fermi level wherever it is, and we can see what happens. What's the relation between the excess electron concentration and the excess hole concentration? So this is basically, again, I said excess in context of the intrinsic level. So it's the electron concentration, if it is N type doped, is greater than Ni. If it is P type doped, it is greater than Ni. It's not the excess concentration as the concentration generated because of some external stimulus. So let's keep the excess concentration aside for the time being. Let's call it's in extrinsic semiconductor, and the electron concentration for the extrinsic semiconductor, hole concentration for the extrinsic semiconductor. Now if you write the excess or write the electron concentration in terms of the intrinsic Fermi level, what we can do is we can divide this relation EC minus EF into EC minus EFI plus EF minus EFI. So EC minus EFI, the relation with EC minus EFI is something you remember. That's basically our intrinsic electron concentration, and EF minus EFI is basically the delta which tells that how much the Fermi energy level has shifted away from the intrinsic Fermi level. So if you rearrange this, you do the maths, what you find is one of the term which is NC exponential minus EC minus EFI divided by KT, and this is nothing but Ni. So what you get, N naught equals to Ni times exponential of EF minus EFI divided by KT, and if EF is equals to EFI, then N naught equals to Ni. But if EF is greater than EFI, then N naught is greater than Ni. Okay, so here N naught becomes a function of EF minus EFI. As EF shifts away from EFI towards the conduction band, the N naught will increase exponentially above Ni. Similarly, we can write a similar relation for P naught, and in that case basically you can write Ni is same for both N type and P type, doesn't matter. So you can write, in this case it's EF minus EFI with this negative sign. So as EF shifts away from EFI towards the valence band, so as this becomes more and more negative, the whole concentration in that material will exponentially increase above the Ni value. Now another interesting thing is that if you take a product this two, N naught and P naught, right, or you take the product of this two, this N naught and P naught, you see that this will cancel out, this and this will cancel out. So what you get is N naught P naught equals to Ni square. And this is something you will get from the previous relation as well. So no matter whether it's a doped semiconductor or it's an undoped semiconductor, whether it's an extrinsic semiconductor or intrinsic semiconductor, this relation is always valid. Okay, so now there's another concept called complete ionization and freeze out. So as I mentioned earlier, that these electrons which were occupied at this energy state, which is ED, you can think of this as the energy state introduced by these phosphorus atoms, and these the phosphorus atom or the arsenic atom, and these electrons which are revolving around the phosphorus atom with a radius close to 25 angstroms. And if you give enough energy, these electrons will dissipate out and move freely in the crystal lattice. Moving freely in the crystal lattice is equivalent to these electrons moving to the conduction band. So as you give enough energy, energy greater than this gap, the electrons will move to the conduction band and they are available to move freely in the crystal lattice. Similarly for the holes, as you increase the energy, these electrons from the valence band will occupy this state, which means they will go and bond, they will form a covalent bond with this particular state which was missing over there, and you get these positive charges or the holes present in the valence band. Now if it is, you can also think the other way. If you have temperature equals to 0, if you go to 0 Kelvin, the more ideal case, the freeze out scenario, you can imagine that all these electrons will stay where they are. All these states will remain empty if it is the conduction band. In that case, the excess carrier available or these additional electrons which were earlier available in conduction band will not be available, or in the case of p-type semiconductor, the excess holes available in the valence band will not be available as they were earlier available, which means that if you significantly reduce the semiconductor device temperature below the freeze out temperature, the excess carriers which were introduced or the doping which was introduced because of the impurity, or these electrons and holes which were introduced because of the impurity, will go back to the donor or the acceptor state, and those electrons and holes will vanish from the conduction band and the valence band respectively till the temperature remains to the freezing point. Okay, so let's see what happens if you dope a semiconductor material with both type dopings. Now this is a very generalized case. I mean, both type doping means you can also dope with just one type of the impurity and use this whole relation for calculating the scenario. But in a generalized case, we are assuming that you dope with both donor and acceptor. Let's say the donor concentration that you introduce is Nd and the acceptor concentration that you introduce is Na. What you see here, you see both the donor states. This is the donor state and this is the acceptor state. Of course, as you saw earlier, we have some thermal electrons and we have some thermal holes. This was responsible for the intrinsic concentration that we discussed earlier. Now, because of these donor states and these acceptor states, now there are certain number of donor electrons which are because of the ionization of the donor states, and these electrons, as you know, will move from the donor state to the conduction band. So as they move from the donor state to the conduction band, they will leave a positive charge back here. Similarly, they may be these ionization of the acceptor states, and the acceptor states will capture electrons, so they will leave these positive charges in the valence band and the negative charge in the acceptor state. So let's assume that the net positive charge in the donor state is Nd, which is the total number of states, minus Nd, small nd, where small nd is the number of states which are not ionized. Similarly, the total negative charge in the system because of the acceptor states is Na, where Na is the total acceptor state, minus small pa, where pa is the number of acceptor states which are not ionized. So if we write down the charge neutrality equation, charge neutrality means any system must be charge neutral. That's the fundamental law. So if a system has to be charge neutral, you have to equate all negative charges with all positive charges. Now what are these all negative charges? All these negative charges are basically the total number of electrons and the total number of ionized acceptors, because they introduce the negative charge. So we add the total number of electrons and the total number of ionized acceptors, and similarly the total positive charge is the total hole and the total ionized donors, the total holes and the total ionized donors. So we rewrite this, which is electron concentration plus Na minus Pa is the total ionized acceptors, and hole concentration plus Nd minus small nd, which is the total ionized donor concentration. Now if you assume that the system is complete ionization is a scenario when none of the acceptor states are available or are not ionized, and none of the donor states are not ionized. So if the complete ionization is there, then the number of states which are not ionized in both donor and acceptor levels will become 0. And if that's the case, you can rewrite this equation, and this becomes N naught plus Na equals to P naught plus Nd. Now you remember, you can rewrite this either in place of N naught, you can write Ni square divided by P naught, or in case of P naught, you can write Ni square divided by N naught. This is because N naught times P naught equals to Ni square. Okay, so we rewrite this equation. Now what you get a quadratic form, because you have, if you rearrange this, if you take this part to the other side, it becomes N naught square minus Nd minus Na times N naught minus Ni square equals to 0. You get a quadratic equation. So you can solve this, based on the quadratic formula, and what you will get a relation for n naught. Of course, you can ignore the other one which will give you the subtraction. So what you get is a relation for n naught, and similarly, if you go for writing n naught equals to ni square divided by p naught, then you get the other form, which is for p naught. So why we did this? This will tell you the total electron concentration if you have a finite number of donor and the acceptor atoms present in the system. Similarly, it will also tell you the total hole concentration if you have a finite number of acceptor and the donor concentration present in the system. Now keep in mind that which formula you must use. If you are using if you start with the electron concentration, then calculate the hole concentration using this formula, then make sure that you use the electron concentration formula only when Nd is greater than Na. Otherwise, you start with the hole concentration. If Na is greater than Nd, then you first calculate the hole concentration, and then using this formula, you calculate the electron concentration. Keep that in mind. You cannot use these two formulas simultaneously to calculate both electron and hole concentration. Okay. So why is this relevant? As I told you earlier, that if the temperature exceeds and temperature is very high, then the intrinsic carrier concentration may become similar to the external or extrinsic carrier concentration, or the dopant that we introduce. So what you see here is, we have temperature and as a function of total electron concentration. Now below a certain temperature, you see the total electron concentration drops dramatically, and that's because of the partial ionization. As the temperature goes below the ionization temperature, all the states are not going to be ionized, all the donor or the acceptor states are not going to be ionized, and because of the partial ionization, the electron concentration will fall. But as you exceed the ionization temperature, the electron concentration will remain more or less flat. But as you exceed a certain temperature, or let's say from this point, the intrinsic carrier concentration will also increase, and you may see a point where the intrinsic carrier concentration will start contributing to the total electron concentration, and then there may be a point where the intrinsic carrier concentration will become similar to the total electron concentration, and that's the point when the device will start behaving differently than you assumed. You assumed your device behavior based on a certain fixed doping concentration in different regions, but as the temperature goes up, the intrinsic carrier concentration increases, and that will significantly increase the total electron concentration above the point you assume, which is this point while designing the device, and therefore the device behavior in this region would be very different than what you started or what you designed for, and possibly the device will not behave as it was supposed to behave. Okay, so we can rewrite some of these things in terms of the position of Fermi level. So for instance, you can start with the electron concentration. There's a relation that we have seen. The electron concentration is a function of the gap between the conduction band and the valence band, conduction band and the Fermi energy level. So if you rewrite this, if you rewrite EC minus EF, what you get is KT ln NC divided by N naught. And if ND is greater than Ni, which means the external doping that we introduced, if this is N-type dopant or the dopant donor impurities, if the donor impurities are far greater than Ni, then you can write N naught equals to Nd. This we can see from the previous relation. Let's say if this is the relation, if this is the formula, and let's say if Na equals to 0, so what you get Nd, you get N naught equals to Nd divided by 2, plus this also becomes 0, and if this is significantly smaller than Nd, we can ignore that, and so it becomes under root of Nd divided by 2 whole square. So this becomes Nd by 2 plus Nd by 2, so N naught close to Nd. Of course, there was a small factor or because of the Ni, but we are ignoring that because Nd is significantly greater than Ni. So if N naught is if Nd is significantly greater than Ni, you can write N naught to be equal to Nd. So from this relation we can change N naught to Nd, and therefore you can write Ec minus Ef equals to Kt ln Nc by Nd. So if you know the doping, you can calculate the Fermi energy position, right? Similarly, you can write Ef minus Ev, which is the Fermi energy position in reference to the valence band for a p-type semiconductor, and in that case the whole concentration is going to be changed by Na, which is the donor, which is the acceptor concentration. So to summarize, for n-type semiconductor we have relation for N naught. If you know the difference between the Fermi level and the intrinsic Fermi level, we basically get Ef minus EFI from this relation, right? And this will tell you, so if N naught equals to Ni, which is again going back to the intrinsic case, Ef is EFI. That's what we saw in the previous case, right? Similarly, for the p-type semiconductor, you can write the same relation. For whole concentration, you can write that in terms of difference between Fermi energy level and the intrinsic Fermi energy level. And you can rewrite this, the difference between intrinsic Fermi level and the Fermi level is Kt ln P naught divided by Ni. And as I said, if this is heavily doped n-type and n-type doping is greater than Ni, you can also write this as Nd, and in this case you can also write this as Na. Okay, so if you want to see how these things changes, this relation will, or this plot will help you how the Fermi energy level changes. So far you have seen you have understood things in this fashion, that for n-type semiconductor the Fermi energy level is above EFI and close to conduction band, and for p-type semiconductor Fermi energy level is below EFI and close to the valence band. But let's say if you change the doping concentration, let's say if you change the acceptor concentration, what you see is that the Fermi level, this is the Fermi level, so the Fermi level will get closer and closer and closer to the valence band. This is the valence band level. So as you see, this gap between the Fermi level and the valence band would reduce as you increase the doping concentration or the acceptor concentration. Similarly, if you increase the donor concentration, this gap will reduce. As you increase the donor concentration, this gap is going to reduce, right? Now, what happens if to donor state, which was that discrete energy level, when the donor atoms come closer to their respective wave functions and they start overlapping? That's the scenario when it's called degenerate state. So when basically two donor states, let's say you had one phosphorus, you had another phosphorus, and when they get closer, their wave functions will overlap. And if their wave functions overlap, that's the scenario when you call it a degenerate doping, right? So that's the case when the Fermi level will shift into the conduction band, or in the other case the Fermi level will shift into the valence band, and accordingly the doping concentration or the total concentration of electrons and the holes is also going to be modified. Okay, so before I close, let's look into some of the numerical problems. Let's calculate the intrinsic carrier concentration in gallium arsenide at temperature 300 Kelvin and temperature 450 Kelvin. So we have to calculate the intrinsic carrier concentration. You remember the intrinsic carrier concentration was a function of the density of state in the conduction band and the valence band, and it's also a function of the temperature. So what do we do? You remember the relation Ni square equals to Nc Nv exponential of band gap and Kt, right? So this is what we are going to do here. We have NC value, we have NV value. We have to calculate it for 300 and 400 Kelvin. You need KT, so you know KT value at 300 Kelvin, and as we did earlier, we can calculate the KT value at 400 Kelvin. So now we feed all these parameters in this relation that we derived earlier, Ni square equals to Nc Nv exponential of minus Eg divided by Kt. For 300 Kelvin, you feed all the values here, so you get the Nc value, the Nv value, the band gap for the gallium arsenide, and the Kt value. And for 400 Kelvin, you feed the Nc Nv, of course, the multiplication factor and the Kt value, right? So if you do that, you get the Ni value at 300 Kelvin and the 450 Kelvin. And as you notice, as I had told you earlier, that the temperature, as the temperature increases, the Ni value will increase, and that's what you also see from this numerical problem. Okay, so the other problem is that a silicon device with N-type material is to be operated at 550 Kelvin. At this temperature, the intrinsic carrier concentration must contribute no more than 5% of the total electron concentration. Determine the minimum donor concentration that requires this specification. So you have got the ratio of intrinsic carrier concentration and the total electron concentration. So intrinsic carrier concentration is 5% of the total electron concentration. You also know the relation between intrinsic carrier concentration and rest of the parameters. So the temperature there, you can calculate the band gap. So let's feed the values here. What you get is the intrinsic carrier concentration. The intrinsic carrier concentration turns out to be 3.2 into 10 power 14 per centimeter cube. And so now the condition is that the intrinsic carrier concentration should be less than 5% of the total electron concentration, which means N naught equals to 20 times Ni, right? Now we looked into this relation, so we can change that. N naught equals to 20 times Ni. There is no Na, so Na equals to 0 here. We use the relation that we derived in the previous slide. So you feed all the values, Nd divided by 2, it's Nd minus Na divided by 2, so Na is 0, so Nd divided by 2, and then Nd divided by 2 square plus Ni square equals to 20 Ni. You solve this quadratic relation, and what you get is Nd equals to 1.39 into 10 power 15 per centimeter cube. Okay, so let's stop here. We have understood the electron distribution and the electron and hole distribution in relation to the Fermi energy in this particular module, and hope you have understood the concept of intrinsic carrier or intrinsic semiconductors, and therefore intrinsic carriers, and the concept of extrinsic semiconductor and the extrinsic carriers, the concept of doping, and then in that sense how to derive the relation for electron concentration, hole concentration in relation to the Fermi energy, intrinsic Fermi energy, and so on. And now we will try to study the semiconductor material in non-equilibrium condition in next modules, and we'll use all this understanding to start understanding PN junctions and diodes and transistors in subsequent modules. So thank you very much.